In this video, I want to talk about domain-specific languages. And to start, let's look at a bit of computer history. This is one of the first computers used in a commercial context. It's called a Leo, built by scientists and engineers from Cambridge University for the Lyons Baking Company. This was in use in about 1950 in the UK. And it was used to automate all sorts of aspects of this company's processes. It's remarkable, really, that it was in action at that time. But the people who programmed this had to program in the language of the machine. The people programming it were not the people who were not economists or bakers or transport experts. They were people who had to understand the intricate details of the computing machine. And things have continued like that. Moving to the 60s was the time when the first high-level programming languages like Fortran and Algol and COBOL got developed. But even then, the languages were machine languages at a higher level, admittedly. But they were still, it was the machine that was being programmed rather than writing the programs at the level of the thing that was being modeled. And we've seen a similar thing in the blockchain world, the Bitcoin scripting languages, Solidity, and so on. Tell us an awful lot about the underlying technology, about the underlying machine, if you like. And they're perhaps not as friendly, definitely not as friendly to the user as they might be. So, as programming languages have developed, these general purpose languages have also been supplemented by what people call domain-specific languages. And the idea here is that the language should be closer to the language used in the domain where it is being applied. So the language is close to the language. See here, the people who are talking about financial contracts, for example. And there are a lot of good reasons for doing that. As I say, principally, it means that we can write programs in the language of the user, not of the machine, roughly speaking. So in thinking about domain-specific languages for financial contracts, what we want to do is think in terms of payments. We want to think in terms of deposits being made, perhaps choices being made as part of the contract, rather than thinking in terms of transactions on the blockchain, for example. So we want to try and express things at that higher level. So that's what we're looking for in the language we're designing. But there are other advantages. It's not simply we talk at a higher level. Simply because of the way we design the language, some mistakes can be rendered impossible. Because we can't, for example, think about doing something which has nothing to do with something financial. We can, because we've restricted the language, we restrict what people can write. So that's helpful. We can rule out some mistakes, but also we can then take the programs and we can analyze them in a much more powerful way, a much more accurate way than we could for a general blockchain smart contract, blockchain script, because we've got a small number of constructs. We understand exactly what they should do, and we can do analysis much more easily. Because we know, for example, that a financial contract, as it's modeled in our language, will stop being active after an amount of time. It won't carry on forever. So we can help people, we can give them more useful feedback about what they write than if they've written in a general language. We can also design programming tools that help, and those tools can be designed to fit the DSL directly. So we can make programming easier, more precise, and more pleasant for people. But also, it's a language, but we can get the best of both worlds sometimes by embedding it in a full programming language. So we can use, this is what we do with Marlowe, we embed it in Haskell so that we can selectively use features of the host programming language. And because it's a language, we can run programs and so on, but we can also do other things with them. We can simplify. We can say, oh, can we simplify this contract to this other contract? Do these two contracts have the same behavior? We can ask, for example. And also we can think, and rather than running a contract, we can think of trying to make a valuation of a contract. So because we've got a language here, we were expressing our contracts in this high level way, we can do other things than simply run them. So I hope that gives you a sense of the value of writing a DSL for, in general, and perhaps helps you understand why we wanted to write this DSL for financial contracts in particular running on the Cardano blockchain. Okay, what we'll do next is take a look at what financial contracts look like. And after that, we'll think about how they need to be adapted to run in a blockchain context.